All right, we're going to be investigating local extrema, so local max and local min values in 3 dimensions. So we can see in our picture here, in our 3D model, clearly there's going to be a local max there and a local max there, and below we've got a little bit of a local min. And so what do those look like on a contour map? Well, you know, the local max and the local mins will be like peaks of a mountain or I guess a valley. And what we see is our local max is in fact on our contour map, you know, a bunch of concentric circles where the biggest z value is in the center. So we have our biggest z value and circles going outwards. Likewise, our minimum is the same thing, circles going outwards, where these values, as we get into the center, are getting smaller and smaller and smaller, which result in our minimum value. So we want to look at how do we identify local extrema given some function. Well, let's start off with a little bit of single variable calculus review. So in this function here, which is, if we factored it, so that we can think about its zeros. So in this two-dimensional graph, if I wanted to find the local max and min, or in this case only the local min, the idea of single variable calculus is that the local min is going to occur where my first derivative is 0 and where it changes sign. So my derivative, you know, I'm going to have a negative derivative because my function is decreasing, 0, and then a positive derivative because my function is increasing there. So to find the local max and or min, we find the derivative. We see that this equals 0 when x equals negative 3/2. And then just to be sure whether or not that's a max or a min, we make a derivative chart. So we know that at negative 3/2, my derivative is 0. When it's less than negative 3/2, plugging that into my derivative, we're going to get a negative value. And when it's greater than 3/2, x being greater than, negative 3/2, if I plug a value into x that's greater than negative 3/2, I get a positive value. So that implies that it is a min, and I've found the value of x for which it is a min. We're going to use very similar methods, not exact, but similar methods when we start talking about 3 dimensions. So for single variable calculus, the max or min occurs where the first derivative is a 0 or undefined. What's going to be the equivalent in multivariable calculus? Well, what do we think? Well, possibly when the first derivative with respect to x equals 0 and when the first derivative with respect to y equals 0. Let's think about what that means. Well, if we go back to this image that we have of a 3-dimensional system, at our local maxes and min, so let's just look at one of these. At our local max at this point, both in the x direction and in the y direction at that point, my partial derivatives are 0. Okay, that's the equivalent. So at the local max or min, we could rephrase this slightly different. The function can be approximated as a plane. Well, a function can always be approximated as a plane. So we can approximate the function as a plane at that point that is going to be perpendicular. Well, since fx equals f partial y equals 0, we know that my plane is just going to be perpendicular to the z-axis. So my plane will just be that z equals some z value, whatever z value it is there. So we could say that slightly differently, which is that whenever my gradient, and remember my gradient is fxi plus f partial yj, anytime that my gradient is either 0 or undefined, that's a critical point of my 3D graph. And this is exactly, this is exactly analogous to what we were saying before with single variable calculus. We're just saying that now both derivatives, both partial derivatives, need to be 0 or undefined for there to be a critical point. And we see that both here and there. So if I wanted to analyze the critical points of this function, what do we need to do first? Well, let's think. We could find f partial x, 2x minus 2, and f partial y, which is 2y minus 4. And we need to set these equal to 0. Because when these equal 0, we are going to have a local max or min. So this is going to occur when x equals 1 and when y equals 2. And when x equals 1 and y equals 2, my function, well, just plugging that in, this is what the z value will be. I think it's 0. So my critical point then, therefore, is at when x is 1, because that makes my partial with respect to x 0. When y equals 2, because that makes this 0. And when z equals 0, because that I got from plugging my known points into my function. So here is my critical point. Right now, we can't confirm whether it's a max or a min, but we found the critical point. We will learn later how to identify max or min. Well, let's look at a table of values to start thinking about local extrema. So if we're at the point near, if we're near the point 1, 2, so that's right here, what we notice is that in any direction that we go, increasing x or y or both, no matter which direction we go, our z value increases. Therefore, we can see that 1, 2 is a local min. And these are the values from, or this is the function from the previous page. So one way that you can identify whether or not it's a max or a min is just to, plug a bunch of points around your critical point and see, are my z values getting bigger or smaller? In this case, they're getting bigger, so that means that this is a min. However, there must be a better way to do that so that we don't need to create this huge chart, and we will look at that. Well, another way that we could have confirmed that this is a local min is to take our function and try to re-express it by completing the square. So I've got this x squared minus 2x. I know that what would complete the square there is if I added 1. And x squared minus 4y, so divide negative 4 by 2, square it, we get plus 4. And notice I didn't change my function. Here I've got 1 and 4, and these add up to get 5. But by re-expressing it like this, now I can write my function as x minus 1 squared plus y minus 2. squared. And what shape is this? Well, this is just, a 3D parabola that's been shifted 1 in the x direction and 2 in the y direction. So if we call this y and z and x, we've shifted up 1 in the x and then 2 over in the y. And what we're creating, is a three-dimensional parabola that looks something like that. And we can clearly see here that the minimum is occurring at the point 1, 2, which comes from the transformation that we were able to see once we completed the square. Here's a much better graph, computer-generated graph of the same thing that I just drew. Okay, so let's also be aware that, just general intuition, looking at a function, we can judge whether or not we would expect a max or a min. So here we have this function, and we have z equals negative the square root of x squared plus y squared. So x squared plus y squared, each of those terms are being squared. So we know that x squared plus y squared must be greater than or equal to 0. And as x and y grow, as x squared plus y squared increases, my z value, because of this negative in front, will decrease. So we would expect that z will be as big as possible, so z will have a max when what is true? Well, when my inside is as small as possible. And that's going to happen when x equals y equals 0. So we would expect that that would be a max. Well, okay, let's see what happens when we talk about finding the gradient. Well, f partial x is going to equal, given this function, negative 2x over 2 times the square root of x squared plus y squared. 2's will cancel off. And what makes this equal to 0? Well, that's going to be 0 when x equals 0. And f partial y is exactly the same thing, except it will equal 0 when y equals 0. So therefore, by just doing the math without thinking about what's going on, we realize that we're going to have a critical point at this critical point at 0, 0, 0. And then, will it be a max or a min? We already answered that. It's going to be a max. We know it's going to be a max because of the fact that for any value of x and y bigger than 0, the negative in front is going to make my z be negative. And here's the cone that graph creates. And notice this is just all of my level curves are a bunch of circles that are dropping down. Okay, well, what about this function? We know that f partial x is 2x, which equals 0 when x equals 0. And f partial y is 2y, and that's going to equal 0 when y equals 0. So it seems like, my critical points, it doesn't seem like, but my critical points, or point, is when x equals 0, y equals 0, and putting that in for my function when z equals 0. well, will this be a max or a min? Here's where it would be good to be familiar with some of the more important shapes of graphs. We know that this is going to be a saddle. So this looks graphing this is rather challenging. I'm doing a bad job at it. But luckily the next page has a picture of the saddle right here. And we notice that this is that critical point. It's when both f partial x and f partial y equals 0. But we notice that it's neither a max nor a min. So sometimes when we find critical points, it'll be a max. Sometimes it will be a min, and sometimes it won't be either. And here's what a contour map looks like when it's neither. What we see is that we've got this value of 0 and 0, and we don't have the concentric circles, which are features of a max or min. All right, let's think about this function. It's a little bit tougher for us to do. We want to find the local extrema, so we find the partial derivatives. And we set them equal to 0. So we find out from our first equation that as long as x equals y, my partial with respect to my f partial with respect to x will be 0 as long as x equals y. And my f partial with respect to y is as follows. And this is going to be true this will be equal to 0 as long as x equals y squared. So for these both to be true, we can use substitution. For these both to be true, we know that y must equal y squared. And this happens when y is either 0 or 1. So we also know that x equals y. So the critical points that we have are going to be, when y equals 0, x must also be 0. And if we plug that into my formula, z is 0. And then when y equals 1, x must also be 1. So 1, comma, and then plugging in 1 into this formula, we get -4. So looking on the next page, we have our solutions. They make our gradient function equal 0. And we notice that on our graph, on our contour, we've got concentric circles at the point 1, 1, and 1. Sorry, -4. And what we notice is that my z values are getting smaller and smaller. So I have -1, and then -2, and -3, and -4. So that implies that this is a minimum because my z values are decreasing. And at 0, 0, I've got this cross section here, which is a saddle point. So that, therefore, this is neither or neither. It's up to you. That's it for this video. In this assignment, please watch the following video that looks at some more algebraic ways for us to determine whether a critical point is a max or a min or neither.